Hello, and welcome to Agrosive Physics. Today is day 97, and I'd like to talk about diffraction. Now, we know that light travels in a straight line. That's based on Fermat's principle. And when light hits a surface, it's going to bounce off, it's going to reflect. If light enters a new material, it will refract, it will change directions. Now, one thing that light also does is it diffracts. And what that means is it spreads out behind a boundary if the opening is around the same size as the wavelength. It's the reason that shadows are fuzzy. If light did not diffract, there would be a clear distinction between the edge of a shadow and the surrounding light. What shadows actually have are two parts, an umbra and a penumbra. The umbra is the really dark part, and the penumbra is kind of the fuzzy part that is a mixture of dark and light. So shadows do not have a clear distinction between where they start and end. They kind of fade off because of diffraction. And once again, when light enters an opening, it's going to spread out on the other side of that opening if the size is about the same. Now, all waves are going to diffract, not just light. For example, sound waves will diffract. And if you talk into the opening of a doorway, the sound waves will spread out behind the doorway and actually form a circular wave pattern. So someone standing to the right or left of the doorway will actually be able to hear you, even though if the sound waves just went through the door, only someone in the actual vicinity of the doorway, a straight line path, would be able to hear. If I shine light through the opening, it's not going to form that pattern because the order of the wavelength is so much smaller for light. Wavelength of sound waves is around a meter. Opening of a doorway is around a meter. So sound waves will diffract through the opening of a doorway. On the other hand, light will have an order of magnitude around 10 to the negative 7 meters, or in the hundreds of nanometers. So what will happen is you'll need to have a much smaller opening in order for light to diffract. But when light diffracts through an opening, the straight line pattern will actually form a circular wave pattern on the other side. If you have it really close to the wavelength, you're going to produce a very distinct circular wave pattern. If it's close but not exact, it's going to be less circular. It might be more oval shaped. Now, this principle is based on Huygens' principle. And Christian Huygens said that every point on a wave can be the source of a new wave. So what he basically thought of is what we refer to as baby waves or wavelets. Every point on a wave has the ability to produce a whole new wave, almost like the wave has its own memory of what the full wave looks like. So if a wave enters an opening around the same order of magnitude, it will know that it can produce a new wave on the other side that's circular in nature. That's called Huygens' principle. And he came up with this principle after observing light waves traveling through different openings. Now, the fact that shadows are fuzzy is an example of that. Also, the fact that you can hear a person talking on the other side of a doorway is an example of how sound diffracts. We could do the same thing if we take our fingers and place them really close together like this and try to look at a light source. Once we get to a point where we see an alternating series of light and dark lines, we are actually seeing a diffraction pattern between the different waves that are being created. We could have a single opening where you have a nice circular wave pattern, or you could have multiple openings, and we call that double slit diffraction. If you have two openings and send light through the two openings, you're going to produce a wave pattern that's circular in nature for each opening. Well, those circular wave patterns are going to interfere, just like the speakers did when we talked about interference of sound waves. So what happens is if you have openings that are really small, and when we did this originally, they used this was Thomas Young. He used what it's called Young's double slit diffraction experiment. He took a piece of glass and painted it, and then used a razor blade to make really small openings. He shone light through it, and what happened on the other side is there was an alternating series of light and dark lines, just like with the speakers where there was alternating sounds of loud and soft. So double slit diffraction is an example of diffraction, but diffraction in addition to interference as well. So you can have a single wave formed which is great if you just want a single circular wave on the other side of an opening, or you could have the waves interfere with one another and have double slit diffraction. Now, I wonder what would happen if we had more than 2 openings. I guess we'll talk about that tomorrow. That's all the time we have for today. Basically, diffraction occurs when we have an opening about the same order of magnitude as the wave, and it will spread out on the other side and produce a circular wave pattern. It's why light going through a really small opening, like putting your fingers close together, diffracts. Why sound waves diffract through the door opening, and even why you can have better reception for AM radio stations up in a mountainous region. When you pass by a mountain, you might be able to have an AM station come in a lot clearer than an FM station. And the reason that's the case is because AM radio waves have a huge wavelength, sometimes in the order of thousands of meters. Well, what happens is the sound waves travel in between 2 mountains. Well, mountains are thousands of meters apart, and they diffract on the other side. So the next time you're traveling in a mountainous region, like in New York State, possibly the Adirondacks, put on the AM radio stations once the FM stations are harder to receive. And you might be able to find that your AM station from home is still coming in clear, even though you're hundreds of miles away. And that's because of diffraction. The size of the opening matters. And even though AM radio waves are hundreds or thousands of meters long, it can diffract in between 2 mountains. Just the same as sound waves diffract through a door opening, and the same as why you have to have a really small opening for light to diffract. And you'll actually see the diffraction pattern through your fingers, if you have them close enough, where you have alternating series of light and dark lines. You're getting interference patterns. And you can do that anywhere you want. Well, that's it for today. I thank you, and we'll move on to diffraction gratings tomorrow. All right. Now, diffraction is when a wave spreads out on the other side of a boundary. And diffraction is not just occurring with light waves. Now, for example, if we have a light wave coming in and it hits an opening, and the opening needs to be about the same order of magnitude. Remember, when we talk about wavelength of light, it's around 450 nanometers to 700 nanometers, violet to red. And that also equates to 4.5 times 10 to the -7 meters, or 7 times 10 to the -7 meters. So this opening needs to be in the nanometer scale. But what will happen is when it gets to this point, it'll spread out on the other side, like this. And there's a famous experiment by Young called the double slit experiment. And I'm not going to draw this to scale, but basically what he did is he set up 2 openings, really small. He had a black piece of glass. It was painted black, and he scratched really thin lines on it with a razor blade. What that did is it produced a wave pattern, circular wave pattern, through the one slit, and it did another one through the other slit. Now, remember, when you have 2 wave patterns that are interfering with each other, you're going to end up with an interference pattern. And he saw that there were areas of light and dark on the screen, and they should have been symmetric. But that was the beginning of working with diffraction gratings. And diffraction gratings are another way that we can break light into its components. So we can break light into its components using dispersion, which is based on refraction. And now we could also break up light by diffraction. But unfortunately, with a single opening or 2 openings, we're only producing 2 waves, 2 baby waves. And Christian Huygens discussed the fact that this pattern, was because of these wavelets. So every part of a wave remembered, if you will, it had like its own wave DNA, and was able to create a new wave from that wavelet. So what we have here is two waves being created. We could have a triple slit if there was another opening, and that would produce another set of waves, and then you'd have more interference. And what Young found is that as the interference became more and more dramatic, these lines became more defined, and you were actually able to break the light into its components as well. And we use that when we deal with spectroscopy, where we're finding the bright line spectra of elements. So we're able to break up the elements into their fingerprints, if you learned about that in chemistry, determining what light is released when electrons jump from higher to lower energy levels inside the atom. Now I'll show you a couple of examples of diffraction gratings where we increase the number from 2, which is what Young started out with, to the hundreds or the thousands of openings, creating thousands of baby waves and then breaking light into its components. Now, using geometry, we can actually come up with the way to determine how far apart the pattern will be if we do have Young's double slit equation. Now, if we have this as a diffraction grating, and we have light coming in, has a certain wavelength, what's going to happen is going to create a lot of these waves. They're going to interfere, and then they're going to create a pattern over here. This is the pattern of light. Now, there's actually a mathematical way that we could figure out different variables in this diffraction setup. If we have a diffraction grating, we have light source coming in. Of course, once the waves hit this diffraction grating, which may have hundreds or thousands of opening, we're going to have thousands of baby waves. They're going to interfere and produce a pattern on the screen here. So what will happen is you can determine different characteristics. For example, how wide the slits are from one another, what the wavelength of the light is, or maybe predict what the pattern will look like. The equation is simply x over L equals lambda over D. X is the distance between the bands, and that's on the pattern, so all you'd have to do is measure this value here. L is how far away you are from the screen, so L is slits to screen. D is the distance between slits, so this is based on D here. And then lambda, well, we know what lambda is. It's the wavelength of the light. So we can use the extra large lambda equation in order to figure that out. Now what I have is the laser again. And what I'll do is I'll show you what happens when I shine this through a diffraction grating. I have a diffraction grating here which has hundreds of lines per inch. Of course, they list it in the English units. And what you'll notice is if I shine the light onto this screen and I move the diffraction grating up or down, we're going to produce multiple waves. We're seeing more than one dot. As you see more than one dot, that's showing the diffraction. You're seeing the interference pattern on this screen here. Single. Now we're getting multiple. Single. Multiple. Now the size of the pattern will be based on the distance between the slits. And you'll notice you have X and D here. They're on different levels of the equation. So we're going to have a different variable. If we have the same laser, we keep L constant, we change the D. If we increase D, we're going to decrease the X. So we have an indirect relationship. And we can see that with different types of diffraction gratings. The ones I have here are standard, but we could have different sizes as well. So that's the diffraction equation.